You probably drive past them like all the time on your commute.
Yeah, the massive steel storage tanks.
Right. Just towering over chemical plants or paper mills or refineries. You glance at them and, well, you just keep driving.
They just blend into the background of the highway.
Exactly. But what you probably don't realize is that those metal behemoths are actually breathing.
Literally breathing.
Yeah. They are inhaling and exhaling all day long.
Yeah.
And if they inhale the wrong kind of air, global manufacturing literally grinds to a halt.
Which is pretty terrifying when you think about it.
It really is. So our mission today is to uncover the hidden lungs of heavy industry. We're doing a deep dive into a highly unusual, oddly fascinating source.
Yeah, the technical specification sheet for decase rebuildable steel breathers.
Right. Which sounds dry, but...
But it's the unsung technology that keeps the modern world moving. I mean, without these devices acting as a barrier, the industrial machines we rely on would basically drown in their own environments.
Okay, let's unpack this. Because realizing that these massive steel storage tanks breathe, it completely changed how I look at industrial sites.
It's a total paradigm shift.
It is. Because, okay, when you have a massive reservoir holding, say, thousands of gallons of fluid, whether it's diesel fuel or some specialized hydraulic oil, and you pump that fluid out, you're creating a massive physical void inside the tank.
Right. And nature abhors a vacuum.
Exactly. To prevent the steel walls from, like, literally buckling inward under atmospheric pressure, ambient air from the outside has to rush in to replace that lost volume. The tank inhales.
And that inhalation is exactly where the catastrophic danger lies.
Because of what's in the air.
Exactly. Think about the physical reality of the environments where these massive tanks live. We're talking about pulp and paper mills. We're talking about chemical plants, power generation facilities, steel manufacturing.
Right.
The ambient air in those places is, well, it's not a pristine mountain breeze.
No, I imagine, like, a paper mill is basically a humid soup of airborne wood fibers, steam, and, chemicals.
You're spot on. It is heavily contaminated. It's filled with microscopic dirt, abrasive industrial particulate, and, crucially, extreme moisture. High humidity.
Just wet, dirty air.
Right. And if a massive diesel storage tank or a highly sensitive hydraulic reservoir inhales that wet, abrasive air directly into its system, the machinery dies.
Wow. Just from the air.
Just from the air. The water causes the oil to degrade, it loses its lubricity, rust forms on the inside walls of the tank, and microscopic grit basically shreds the internal pumps.
Oh, man.
Yeah, it is a catastrophic breakdown just waiting to happen.
And that is where these decase rebuildable steel breathers come in. They are the highly engineered lungs sitting right on top of these tanks.
Exactly.
And by the end of this deep dive, you are going to look at the industrial landscapes around you completely differently, knowing the invisible molecular warfare happening just to keep those machines alive.
It's a brilliant piece of preventative engineering, it really is.
So now that we understand the physical reality of why these massive tanks have to breathe, let's look at how this breather actually purifies that toxic wet air.
Okay.
Because I was looking at the anatomy laid out in the specs, and it lists a 1-micron absolute filter efficiency.
Mm-hmm.
So I'm visualizing this pleated microglass filter acting like a heavy-duty N95 mask for a power plant, right?
That's a great way to picture it.
It's catching all the physical dust, the grit, the solid particles down to a microscopic level.
Yes, and the word absolute is critical there.
Oh, really? Why?
Well, it means exactly that. Under strict testing, essentially nothing larger than 1 micron is getting past that microglass barrier.
Wow.
For context, a human hair is about 70 microns thick.
Okay, that is incredibly small. So the N95 mask analogy works for the physical dirt.
Yeah.
But here's my pushback on that.
Okay, let's hear it.
You can't just filter out water vapor with glass.
Right.
Like if you wear an N95 mask, it gets damp when you breathe through it because vapor passes right through the fabric. So a microglass filter, no matter how microscopically fine, isn't going to stop pure humidity from rushing right past it into a hydraulic tank.
You are entirely correct, and that is exactly why the microglass filter is only the first line of defense.
Okay, so what's next?
Well, what's fascinating here is the second layer, the desiccant.
Ah, the desiccant.
Right. Once the violent rush of air passes through that 1-micron filter and is stripped of its solid particles, it has to survive a chemical gauntlet. It moves through a thick bed of highly engineered drying agents.
The desiccant, like those little packets you find in a new pair of shoes or a bottle of vitamins.
Conceptually, yes, just scaled up to an industrial level.
Right, right.
But the physics of how it works is where the magic happens. These chemical agents work through a process called adsorption. With a D...
Wait, don't you mean absorb with a B? Like a sponge soaking up water?
No, and it's a vital distinction.
Really?
Yeah, absorption with a B is like a sponge soaking up a spill. The water enters the actual volume of the material and causes it to swell up. Adsorption with a D is entirely different. It's a surface phenomenon.
Okay, how so?
Think of it more like static electricity holding dust to a television screen.
Oh, interesting.
Right. The water molecules in the humid air are physically drawn to and trapped on the massive surface area of the microscopic pores on the outside of the desiccant beads.
So they don't soak it up like a sponge.
Exactly. The beads themselves don't swell or change shape. They just grab the moisture out of the air and hold onto it tightly on their surface.
So the air is just stripped bone dry as it runs this chemical minefield.
Essentially, yes.
And the spec sheet actually reveals a whole menu of these desiccants depending on what kind of toxic air your plant breathes. Like the standard medium is silica gel, which handles general moisture perfectly.
Right, that's your workhorse. But they don't stop there. They also offer activated carbon, molecular sieve, and activated alumina.
Okay, wait, explain the molecular sieve because that sounds like something straight out of a sci-fi movie. How is that different from standard silica gel?
Oh, a molecular sieve is incredible. It is a synthetically produced crystalline structure with pores of a very exact, uniform size.
Okay.
It literally acts like a microscopic bouncer at a club.
A bouncer?
Yeah. The pores are precisely sized to match the angstrom width of a water molecule.
No way.
Yes. So as complex industrial gases and humid air rush past, the sieve traps the water molecules perfectly while completely ignoring other chemicals.
That is wild.
It's used when you need extreme targeted dehydration in very specific chemical environments.
Yeah. And all of this microscopic filtration and chemical absorption is happening inside an incredibly tough shell.
Oh, yeah. The housing is intense.
Right. The specs detail this rugged steel housing, which you can get in standard carbon steel, or if you're in a highly corrosive spot, say, like a coastal refinery taking on saltwater spray, you can upgrade to 304 or 316 stainless steel.
You have to, yeah.
And the temperature range it has to operate in is just brutal.
It has to be. I mean, industry doesn't stop for the weather, and these lungs are exposed to the elements 24/7.
Right. The breather has to function flawlessly from negative 20 degrees Fahrenheit. Which is, by the way, the temperature where standard hydraulic oil literally turns to a thick, useless sludge.
Right.
All the way up to 220 degrees Fahrenheit, which is hotter than boiling water.
Which is extreme.
Yeah. That's negative 29 Celsius to 104 Celsius. It has to survive a freezing winter night in North Dakota or the blistering radiant heat inside a steel mill.
And it has to do all of that while remaining chemically compatible with whatever fluid is sitting just inches below it inside the tank.
Right, right.
The specs note these units are compatible with all mineral oils, most synthetic oils, and diesel fuels.
It's a lot to ask of one device.
It is. You have this incredibly delicate molecular balancing act, stripping microscopic water vapor out of the air, happening inside a heavily fortified steel vault that's being blasted by extreme heat, freezing cold, and highly corrosive fumes.
It's a perfect intersection of brute force and microscopic precision.
Nicely put.
But, understanding the anatomy of a single breather is one thing.
Yeah.
When you look at the physical scale of these operations, it reveals the sheer magnitude of industrial fluid dynamics.
Absolutely.
We're moving from the molecular science of the desiccant to the physical sizing of the machines. And, well, here's where it gets really interesting.
You're looking at the product codes, aren't you?
Yes. The product codes and the size variants. I mean, the list spans from the tiny DCRS3 all the way up to the massive DCRS200.
Quite the range.
Yeah, I'm looking at the dimensions here. The RS3 is the baby of the family. It's about 11.5 inches tall, holds 3 pounds of desiccant, and traps a modest 0.14 gallons of water.
Okay.
Basically a heavy coffee mug's worth of water, which makes total sense for a small hydraulic reservoir.
All right, a very manageable size for standard slow-moving equipment.
But then you look at the big boss at the bottom of the chart, the RS200.
The giant.
It is 42.8 inches tall. It's almost 4 feet. Why on earth do you need a steel industrial breather the size of a small child?
Well, to understand why a tank needs a lung the size of a small child, you have to look at the application sizing recommendations, specifically the maximum airflow.
Okay, airflow.
Massive bulk storage tanks aren't just casually sipping air. When they're being emptied to fill transport trucks or fuel massive factory processes, they are violently gulping it.
Gulping. Okay, how much air are we actually talking about?
The specs show that for these larger systems, you might be dealing with airflows up to 270 cubic feet per minute.
Let's visualize that. How fast is 270 CFM physically? Like, what does that look like?
Okay, think about a typical bathroom exhaust fan in your house.
Sure.
That might pull, say, 50 cubic feet per minute.
Okay.
Now imagine more than 5 of those fans running at maximum speed, forcing all of that air through a single steel pipe on top of a tank every single minute.
Wow.
When thousands of gallons of fluid are pumped out of a bulk storage tank at high speed, a massive vacuum is created instantly. 270 cubic feet of wet, dirty, outside air violently rushes in every 60 seconds to fill that void.
That is terrifying for the machinery.
It is. And if that air is humid, you are dragging actual gallons of water straight into your expensive fluid system.
Which perfectly explains the insane capacity of the RS200. Because the sheet says this single unit holds a staggering 200 pounds of desiccant inside its steel housing.
200 pounds.
And its maximum water absorption capacity is 9.5 gallons.
Just try to picture that physically.
Yeah, picture 9.5-gallon jugs of milk sitting on your kitchen table.
It's a lot of liquid.
That is the amount of pure water vapor this single steel cylinder is pulling out of thin air, just from the invisible breaths a tank takes before the chemical beads are fully saturated.
It's amazing.
36 liters of water trapped from the invisible air.
It really gives you a profound respect for the sheer volume of moisture hidden in the air around us and the massive scale at which heavy industry operates.
It really does. But thinking about a 200-pound cylinder full of trapped water brings up a really practical human problem.
Oh, for the maintenance crews?
Yeah, because these massive RS200 and RS150 units are built from heavy-duty welded steel, and they handle such immense volumes of contamination, they obviously aren't disposable.
Right.
You don't just unscrew a 4-foot steel cylinder and throw it in the dumpster when it's full of water.
No, the name itself gives that away, right? The rebuildable steel breather. The steel housing is a permanent fixture bolted to the tank. You have to maintain the chemical ecosystem inside of it.
And that's exactly where my mind went, to the physical reality of the poor maintenance worker.
It sounds awful, doesn't it?
I was looking at that 200-pound desiccant capacity. If I'm a maintenance worker standing on a narrow metal catwalk 40 feet in the air wearing thick safety gloves, how do I even lift 200 pounds of saturated, waterlogged chemical beads out of this tube without throwing out my back?
You don't.
Wrestling, that sounds like an absolute ergonomic nightmare.
You're touching on a crucial aspect of industrial engineering. It actually has to be usable by human bodies in terrible conditions.
Right.
The engineers had to design around human ergonomics. For units above the RS-25, they don't just pour the chemical beads directly into the steel housing like cereal into a bowl.
Okay, thank goodness.
The desiccant is smartly packaged in 25-pound modular polypropylene bags.
Oh, that's so smart.
And those bags have heavily reinforced built-in handles.
Right.
So instead of a worker trying to awkwardly shovel out 200 pounds of wet, heavy beads on a catwalk, they just unbolt the steel lid, grab the handles, and pull out these modular 25-pound bags one by one for easy, safe removal and replacement.
Okay, that definitely saves the worker's back. But here's the next logical problem.
What's that?
How does that worker even know it's time to climb up that 40-foot ladder and change the bags? Like, you can't see through a 1/4 inch of solid steel to check if the beads are full of water.
Oh, this is perhaps one of the most elegant design choices in the entire specification sheet. The visual cue, the sight glass indicator.
Yes, I saw that. Right on the front of the heavy steel housing, there's this little window. And the spec sheet explicitly says the silica gel positioned right inside the sight glass changes color. It goes from blue to pink when the unit reaches its maximum moisture capacity and requires rebuilding.
Exactly.
So the machine literally blushes pink when it needs attention.
That's a perfect way to put it. Yes, it blushes.
I love that.
A deep blue color means the desiccant is bone dry and actively standing guard, protecting the tank. A bright pink color means the chemical gauntlet has absorbed its maximum capacity of water, those 9.5 gallons in the case of the Big Boss units, and it's time for a rebuild.
It is such a remarkably simple analog communication tool in the middle of a highly complex, heavy industrial setting.
It's brilliant.
Right. A worker doesn't need to hook up a laptop to run a diagnostic test. You can just walk past the tank on your daily rounds, look up, see blue, and keep walking.
Precisely.
If you see pink, you know immediately it's time to order a rebuild kit. And figuring out the naming convention for these rebuild kits from the spec sheet is actually really intuitive.
It is entirely modular, which keeps supply chains moving efficiently.
Exactly. The sheet shows that you just swap an X for your specific model number.
Mm.
So if you're replacing the whole internal guts for any model, the part number is just DCRSXRK.
Mm.
But if you accidentally dropped a wrench and broke that little glass window on your massive RS-150 unit, you don't buy a whole new breather.
Right.
You just order a sight glass cartridge by asking for a DCRS-150 SG1.
You are modularizing the maintenance. You aren't replacing the expensive steel rib cage. You are just replacing the consumable organs inside.
Right. And the list of those rebuildable organs is extensive, which allows for total customization.
Very true.
You've got the 1-micron microglass filter elements we talked about, the modular 25-pound Desiccant bag sets, foam pad inserts to keep all that internal media secure against the violent rush of air.
Yeah, you need those.
And then there are the gasket seals. This is another area where you really have to match the chemistry to the environment.
Oh, the gasket seals are absolutely critical because a tiny leak defeats the entire purpose of the lung.
Right. The standard gasket material listed is Buna-N rubber, but they also offer Viton, EPDM, and SBR rubber gaskets.
Correct.
Why would a plant manager need to specify Viton over standard rubber? Like, what's the difference?
Because of the violent chemical realities we discussed earlier, Buna-N is fantastic for standard mineral oil. But say your massive hydraulic system runs on a highly aggressive synthetic phosphate ester fluid.
Okay, which is used where?
That's common in power plants for fire resistance.
How's it?
The fumes from that synthetic fluid will literally attack standard Buna-N rubber, softening it until it dissolves into a sticky, useless goo.
Yikes.
Right, and when the seal breaks, wet air rushes in, the system dies. Viton, on the other hand, is a specialized fluoroelastomer.
But what?
Fluoroelastomer. It essentially laughs at harsh corrosive chemicals and extreme heat. By choosing a Viton gasket, you ensure the lung remains hermetically sealed to the tank no matter what toxic fumes are swirling around it.
Man, you are essentially giving the industrial lung a highly customized, complete tissue transplant precisely matched to its environment while leaving the indestructible steel rib cage perfectly intact.
Exactly. It's really elegant. But before we wrap up our analysis of this document, there is a final critical technical recommendation hiding right at the bottom of the spec sheet from Desiccant.
I saw that. The manufacturer explicitly recommends the use of a pressure relief valve on any tank or storage system.
Yes.
Why is that so important to highlight here? Like, why focus on that?
Because it reminds us that these mechanical lungs do not exist in isolation. They are part of a larger, incredibly carefully balanced pressurized ecosystem.
Okay, makes sense.
The breather perfectly handles the normal inhalation and exhalation of air to compensate for the fluid being pumped in and out. But what if there is an unexpected, violent pressure spike inside the massive steel tank?
From what?
Say, from a sudden, extreme temperature surge that causes the fluid to rapidly expand.
Oh, okay.
You need a dedicated, heavy-duty pressure relief valve to vent that spike instantly and prevent the steel tank itself from literally rupturing.
Wow.
The breather manages the quality and the normal flow of the air, but the relief valve manages catastrophic pressure events. They have to work together to keep the machine alive.
It truly is a complete respiratory system.
It really is.
So what does this all mean for you? Obviously, you listening right now will probably never need to go out and purchase a 4-foot-tall DCRS-200 steel breather.
No, probably not.
You probably aren't going to be hauling 25-pound bags of blue silica gel up a freezing catwalk in North Dakota anytime soon.
Unless you have a highly specific and probably very expensive set of weekend hobbies.
Fair point. But the reality is, your daily life is entirely supported by these hidden breathing systems.
Absolutely.
Every crisp piece of paper you write on from a massive pulp mill, every structural steel beam in the office building you work in, the diesel fuel powering the transport trucks that deliver your online packages, all of it relies entirely on these heavy-duty industrial lungs.
It's all connected.
Without them quietly filtering out microscopic dust and trapping literal gallons of invisible water vapor, the massive machines that build our modern world would simply drown in their own environments. They would rust, degrade, and just grind to a halt.
It is a striking testament to how fragile even the heaviest, most brutal industry actually is at a molecular level, you know? And the extreme, meticulous engineering required to keep it all running seamlessly in the background.
It really is. It shifts your entire perspective.
Yeah.
And it leaves me with this one final, slightly unsettling thought.
Oh.
Yeah. If our massive, rugged, heavy-duty industrial machines require such precisely engineered, carefully monitored, color-coded lungs to filter out invisible moisture and microscopic toxins just to survive a few years in their environment.
Yeah.
What does that tell us about the invisible quality of the air we are constantly breathing into our own lungs every single day?
Yeah, that is definitely something to think about.
Thanks for joining us on this deep dive. We'll get you next time.